All right, AP Physics students, now, this lesson on optics is much easier to do when you're all in this room, because I'm going to tell you now, I'm going to try and film this without actually being able to see what you see. So I'm just going to kind of set up the camera and hope this works, okay? So stay with me here. So I'm going to come back here so I can kind of see what's going to happen. Now, what that window is basically doing is, you can kind of see me, is acting as a mirror. So it's kind of cool if you think about what's happening. So the light photons are being emitted from the lights. It's hitting my shirt. It's bouncing off. It's hitting that glass. Part of that is being reflected back, and I'm seeing it in my eyeball. You are seeing it through the camera. So the path that this is taking is from the light. The photons are hitting me. They're bouncing off of me. They're going towards the light. They're going towards the window. They're bouncing off the window, and I'm seeing it in my eyeball. Now, here's where this gets weird. So, like, if I raise my right hand, right, put that down, raise my left hand, boom, put that down. So this is where optics get a little bit weird. So I'm seeing me, and visualize this, on a flat mirror. Imagine, if you would, okay, take at least a bit of imagination. Imagine that there was another me on an equal distance on the other side of that, okay? So if that was the case, if there was another me on the other side of that, equal distance. So if I'm like 4 meters away, my duplicate of me would be 4 meters away on the other side. And so we could do this and simulate this type of thing. So if I would raise my right hand, and if there was of me on the other side, if he would raise his right hand at the same time, you couldn't tell any difference. Everything would be symmetrical. If I did this, he would do that. Now, when you look at mirrors, and this is, well, for now we're just going to deal with flat mirrors. We'll deal with curved mirrors later. So I can see the camera, right, because I'm in line with this. Now, if I move over here, now I can't see, and this is where you have to take my word on this. At this point, I can't see the camera, okay, and you all can't see me. But if I move over a little bit, okay, to here, now I can see the camera, and you all can at least see part of me. So as I move over farther, right, now you can see me. If I keep moving over here, you can still see me because I can still see the camera. Now, if I go over here, I can still see the camera. But if I go far enough out of view, I can't see the camera in that reflection. And now you guys can't see me. So when you're looking at a mirror and you're seeing a reflection, there's a limit to what you can see in the reflection of that mirror. So if I'm over here, now, here's the other thing about the K-State thing. So if you notice that the lettering on my K-State sweater is backwards. It isn't inverted on like an axis like this. It's inverted on, if you think of it like a y-axis. It's not inverted on an x-axis. So this is why if you look at, like, if you've ever seen an ambulance in your rear view mirror and they have ambulance written there, they have ambulance backwards so that when you see it in your rear view mirror, it looks like it normally would, okay? So here's what I want you to get out of this. You're seeing me because that light is bouncing off, but there's a limit. So if I move over here, you can't see me. If I move over here, you can't see me. But if I'm within the axis of these angles, which I'll explain in just a second, then you can see me. Okay, so let me turn this around, and let me stop it. Okay, so one of the cooler things that we've ever been able to do is figuring out how to make light bend. either reflect off surfaces or bend because of lenses. So this is going to serve me a couple purposes. So this is a laser that's being shown on a light. You can adjust this angle. Now, for now, I don't want you to worry about this angle down here. Do not worry about this part. Pretend that this isn't here. We'll get back to it. So right now I want you to pretend that this is like a mirrored surface, okay? So this is why I said don't worry about this part. Imagine this light is hitting here and it's bouncing off. So this is where we treat light as being like a stream of particles. So imagine this is like a stream of marbles that is going to hit here and then it's going to bounce off. Now, the key thing with flat mirrors is that this, what we call the angle of incidence, okay, which is always measured from the normal. This angle of incidence here is going to equal that angle of incidence over there as long as it's a flat surface. Now, if it's a curved, that isn't true. But as long as it's a flat surface, that's cool. So one of the problems that you're going to have on your assignment is dealing with a laser that's being shown down. It's going to bounce off, and then it's going to come over here. And on the problem, it's like you're trying to hit a point on a wall over here, or you're trying to hit a point here. So when you get to this problem, it'll make sense when you get there. This angle here is equal this angle here. So then it's just a matter of trick. So imagine that this is like a right triangle, and this is another right triangle over here. So if you know, like for example, let's say this is 30 degrees, that means that's going to be 30 degrees. So that angle in here is 30 degrees. So then if you know this side of the triangle, two sides of the triangle here, and if you know this angle, you can figure out what that side is over there, or you can figure out what this side is over here. So you're going to have a problem like that. It's like a trick shot. It's like you have a wall here, and you're trying to figure out where you shine that laser to hit a spot on a wall over there. And again, this is easy to do when I have some people that can help me and can hold mirrors. So for now, just take the leap of faith, okay? So you're here, it's hitting, it's bouncing off. Here's what you need to remember about mirrors. This angle here, these angles are going to be symmetrical. That's going to be the key thing. It's when you get to, it's going to be question number 6 on your assignment. Okay, now, here's what I also want you to see. Now I want you to focus on this angle. So now, forget that this angle exists. This ray, okay, sorry about that. It's that time of year, it's cold, brother called again. For those of you that weren't watching the AP Chemistry lecture, that was my brother again. Okay, so here's the deal. So when you look at this light, here's the easiest way to visualize what's happening. So this index of refraction is 1.33. Y'all know what index of refraction is. Bigger this number is, the more optically dense it is, which means the more it slows down light. So visualize this. Here's the easiest way to look at this. So here's this cart, and it's rolling along, right? Now, you're on like dry pavement. This is as fast as you can go. Index of refraction of 1. So imagine that you're coming along like this, and this is like, say for example, relevant to this. Let's say this is snow, okay? So you're going to come along here, and you're going to hit snow. Now, what's going to happen is that this side of the tires is going to get slowed down first. So because it's going to get slowed down first, it's going to change the angle, and then it's going to go like this. Now, the more optically dense you make this, okay? So now you go to like glass. Notice that that angle, that value then has gone up. So what that means is that this is like deep snow, okay? So now you're going to hit it and you got deep snow. And then it's really going to turn it and slow it down and make it come down like this. So the bigger the difference is on your index of refraction, the more it gets slowed down. Now if you reverse it, let's say that you're going to go from a more optically dense medium into a less optically dense medium. Now, so imagine that you're in deep snow, okay? You're in deep snow, and then you hit dry pavement. Well, this wheel here is going to grab first. And so it's going to speed up, and then it's going to tilt it in this direction. So if you're going from a less optically dense medium to a more optically dense medium, then it becomes more severe. If you're going from a more optically dense medium to a less optically dense medium, then it speeds it up. So here you slow down, quick. Here you speed up. There you go. Now, when you're talking about angles, okay, this has this handy dandy little protractor right here. When you're talking about index of refraction, you're always measuring from what's called the normal, okay? So this angle here is like 10, 20, 30, 40 degrees. So this would be like, your angle would be 40 degrees. Not this angle over here, but this angle here. Now, it's the same thing down here. Boom, this would be like 25 degrees. So you've got this normal angle here, this normal angle here. Now, interesting thing happens. Notice what happens if I change this to air. If I change this where both sides are air, in other words, there's no difference in that optical density, notice that there is no change and it just goes straight. Because this is like you're continuously driving on a straight line. But notice as you make this more and more optically dense, you increase that index of refraction more and more. The more and more you increase that index of refraction, the more that light gets bent, because there's more and more difference in the speed of your axles. Boom, whoa, you get slowed way down. It gets bent that way. Or you're going this way, whoo, it always speeds up, goes that way. But here's what you have to remember, and I'll show you the math in just a second. This angle here, when you're talking about angles, it's your angle with your normal. Now, you're going to have a problem on your assignment dealing with, I think it's like a swimming pool, okay? Or there's like you're trying to find goggles or something. There's also one where what you're going to see. So here's the deal. This is also going to be a geometry problem. Like imagine this is the floor of the swimming pool. I think that's what it involves. And you're trying to figure out. You're standing on the edge here. You're trying to figure out where you're going to shine the laser to shine it on a pair of goggles that are down here. So if that's the case, okay, and again, when you're working with these, you have to work with these angles. So again, it's a trig problem. If you can figure out what this angle is, you know, like the depth of the pool, then you can figure out how far you have to shine it here, or you can figure out how far back you have to be here to hit this point so that it illuminates this. Now, I know you're going to have a problem with like a scuba diver. Now, if you're a scuba diver, okay, and one of the things we'll get into is which direction the light is going. So, if you're down below in the water, you're seeing light that's coming in like this, okay? So, when you're looking out, you're going to see light that's coming in like this, but this is where this gets a little bit weird. If you're down here looking at this light, if you trace it back, it looks like it's actually at this point up here, because this hits, boom. But when your eyeball is here, it looks like that laser would be here, okay? So keep that in mind when you get to the boat problem. Now, the math. Come on. Oh, come on. Here we go. So this is what's known as Snell's law. And it's N1 sine theta 1 equals N2 sine theta 2. So let's say, for example, you look at what I was just showing you, and I'll go back to that screen. So let's say that you've got air that has an index of refraction of 1. And let's say that this angle here is 30 degrees. So here's my n value, and it's going to come into water that says 1.33 is this index of refraction. So this would be N1, so you got 1, times the sine of 30 degrees is going to equal into 1.33 times the sine of theta. Now, so because of this equal sign, and if you do the math, let me do a little math here. So you're going to take 1 times the sine of 30 and then divide that by 1.33. So sine 30 1.33. So, and then I'm going to take the inverse sine of all of this to get theta. So I'm going to do a second function inverse sine. This is so much easier than looking at. So I get 22.1 degrees. So what this means is that this angle in here should be about 22.1 degrees. So it came in here at 30, boom, it got slowed down, we bent it closer to normal. So because there's an equality sign, this has a bigger value of n, that means the sine of this has to be a smaller value. So now if I go back to the program and set that up, so if I set that at 30 degrees, okay, so here's my index of refraction, that's 30 degrees. This is like 22, which matches, here's 10, there's 20, okay? So the program matches up with what we said it was going to be. Now, clearly, if I increase that index of refraction even more, to like 1.53, notice that now that angle becomes even smaller. Now, if you're reversing this, if you're going from here to here, you could let this be N1, okay, which would be like 1.6, and then you'd have this angle, which is still going to equal N2 times that angle. Which side you put it on really doesn't make any difference because there was an equal sign. Okay, kids, I'm done. So the assignment's going to be relatively short. And then, like I said, this is much cooler if I can actually do this in person, but it's the best that I can do. So anyway, stay warm. I will send this out on Monday.